What's going on, guys? Justin here, and welcome back to our 15th example video following our course on abstract algebra. Now, today's example video is going to be more examples on isomorphism theorems. So with my introduction out of the way, let's go ahead and get into our first example here. So for this first example, we are going to suppose that we have two normal subgroups of G, M, and N, such that G is equal to M times N. We want to prove that the quotient group of G and M intersect N is isomorphic to G mod M cross G mod N. Great. So let's go ahead and jump into this, and we'll start by defining the following map, which we are going to use for the entirety of this proof. So let's go ahead and define our map in the following way. Let's call this map phi, and phi is going to go from our group G to the 2G mod M cross G mod N. And we're going to use this setup because we want to use the first isomorphism theorem. And to do that, what we're going to want to do is show that the kernel of this function we're about to define is equal to M intersect N, and the image is equal to the entire thing, which is G mod M cross G mod N. We'll also have to prove that this function is a homomorphism. It's very similar to the examples I did in the last example video. So let's go ahead and define the function in the following way, where it takes an element little g from our group G and it maps it in the following way. It maps it to the ordered pair G big M, comma G big N. Great. So let's go ahead and first verify that this is in fact a homomorphism, and then we can take a look at the kernel as well as prove that this function is surjective, which will prove that the image is the entire thing. Great. So let's first verify that this is in fact a valid homomorphism. So let me go ahead and write that we are doing that proof here. So to prove that this is a homomorphism, what we're going to do is we're going to begin by taking two elements from our group G. Let's just call them X and Y. And like I said, those are going to be in G. And then what we're going to want to do is consider phi of X times Y. So let's go ahead and write that. We want to consider phi of X times Y. And we want to show is that this is equal to phi of X times phi of Y. And that will in fact verify that this is a homomorphism. Great. So phi of xy, just applying our definition of phi, is going to be equal to the following. We'll have the ordered pair xy times m and xy times n. Great. But we can rewrite that in the following way using our definitions for cosets. So that will be equal to x times m times y times m. And then similarly, we will have x times n times y times n. But that is exactly the same thing as x times m, comma x times n, times y times m, and y times n. Like I said, that is the product of those two ordered pairs there, but that is exactly the definition of what we would get if we took phi of x and multiplied it by phi of y. So there you have it. We have verified that this function that I've outlined here is in fact a homomorphism. So now what we want to do is look at the image in the kernel. But one of the methods we used in the lecture video corresponding to this example video was that we can prove that the function is surjective to prove what we want to know about the image of the function. So in this case, if we can prove that our function is surjective, we will prove that the image of our function is equal to G mod M cross G mod N, which is all we need for our setup for the first isomorphism theorem. So let's go ahead and get into a surjectivity proof for this function here. And so to prove that this function is surjective, we're going to have to use the two facts that we were given in the problem. The first is that G is equal to the product of M and N, and the second is that M and N are in fact normal in G. So let's go ahead and begin with those facts and see what we can get and see what we can do with them. So first I want to note that for all elements in our parent group big G, and we'll call those elements little g, we can express little g in the following way, and that is as a product of two elements from M and N, just given from the fact that big G is equal to M times N. So that means we can write, like I said, little g as a product of M and N. And this will be for some little m and little n in their respective groups. So like I said, that'll be for M and big M and N and big N. Great. And so next we want to note the following, and that is for all elements of our codomain, let's just write an arbitrary element as G times N and G times N, which like I said is in our codomain, which is G mod M cross G mod N, as well as X and Y, which is in our group big G. We have the following, and that is that X times M is equal to m times n times m, and that is by this condition which we've written up here. But now we can multiply by a creative use of the identity element being n times n inverse, and we'll get n times n inverse times m times n times our big group m there. But by our normality condition, which we are given at the start of the problem, this is an element of m, so that means that this is just equal to n times m. Great. And we can apply a similar argument for our x times m. So like I said, and similarly, we have that y times m can be written as a product of two elements from m and n. And we'll write those as m times n times our big N, but we don't have to use normality here. We can just absorb that little n into our big N here, and that will just give us m times n. Great. So now we have all of our setup that we need to prove that this function is surjective. And so we want to note the following. So we want to note that phi of m prime times n is equal to the following. And so we're going to use the exact definition of our function phi here. And so that what that's going to give us is m prime times n times m for our first input there. And then we'll have m prime times n times big N here for our second input. But now we can use these actions that we found here and get these to be our x and our y as we would need to find that we can map to an arbitrary element of our codomain. So we're going to do that conjugacy action in our first input here. So we'll have that this is equal to n times n inverse times m times n times big M. Once again, we will be absorbing this into our m here. And then here on the right, we can absorb our n into our big N, and we'll be left with m prime times n. And just like we did just above, that means that this will be equal to x times m and y times n. And you can see that we took an arbitrary element from our codomain and we mapped to it using our function, which means that this function is in fact surjective. And like I said, that is equivalent to saying that the image of our phi here is exactly what we want it to be. Our image is equal to g mod m cross g mod n in this case. Great. So now all we have to do is look at the kernel, and if we're able to verify that the kernel of this function is equal to m intersect n, we will have all we need to apply the first isomorphism theorem to this problem here. So let's go ahead and look at the kernel. Let's go ahead and take some element to be in the kernel of phi. Let's just call that little g. And like I said, that'll be in the kernel of our function phi. Great. Well, what does it mean to be in the kernel of phi? Well, that means that phi of our element g must be equal to the identity in our codomain, which in this case would be equal to e times m and e times n. But by the definition of our function, that is true if and only if g times m is equal to e times m, and in parallel that g times n is equal to e times n. Well, we can see that that's true if and only if g times m is equal to m, and g times n is equal to just n, but that's the same thing as saying that g is in m as well as g is in n. And what does it mean for g to be in m and n? Well, that means that g must be in the intersection of m and n by the definition of intersection. So like I said, that g is in m intersect n. So we have an arbitrary element from the kernel of phi, and we've shown that it must be in the intersection of m and n, which is exactly what we wanted to prove. So now we can apply the first isomorphism theorem of groups and see that g mod out the kernel, which is m intersect n, must be isomorphic to the group g mod m cross g mod n. Great. So that finishes this first example off. So let's go ahead and get into our next one. So for this problem, we want to let n1 be normal in g1 and n2 be normal in g2. And we want to show that n1 cross n2 is normal in g1 cross g2, and also that g1 cross g2 mod n1 cross n2 is isomorphic to g1 mod n1 cross g2 mod n2. Great, so let's go ahead and prove this first thing that we have here first, and then we can get into using our isomorphism theorems to take care of the second part. So to begin with this first result, let's go ahead and suppose that we have our setup. So let's go ahead and suppose that we have that n1 is normal in g1, and similarly n2 is normal in g2. Great, and so then we want to take the following elements. Let's go ahead and take g1 comma g2 to be in g1 cross g2, and also the ordered pair n1 comma n2 to be in the group n1 cross n2. Great. And so from here, we want to note the following. And so what we want to note is that G1 comma G2 times N1 comma N2 times G1 inverse and G2 inverse will equal the following. And so by simple multiplication here, that's going to be equal to G1 times N1 times G1 inverse, comma, G2 times N2 times G2 inverse. Great. And so from here, we can use our normality conditions on N1 and N2, which we were given. And so what we want to do is note the following based on the normality of N1 and N2, and that is that G1, N1, G1 inverse must be in N1 by normality, and similarly, we have that G2 times N2 times G2 inverse must be in N2. But that means that our ordered pair that we have here, G1, N1, G1 inverse, and G2, N2, G2 inverse must be in N1 cross N2. But if that's the case, then we must have that N1 cross N2 is normal in G1 cross G2. So that we've proven the first thing that we wanted to prove, and that's that N1 cross N2 is normal in G1 cross G2. So now we can move on to trying to prove this isomorphism here. And so to prove this isomorphism, we're going to have to define a function like we have for all of these so far. And let's go with psi this time. So let's define psi, which is going to go from G1 cross G2 to G1 mod N1 cross G2 mod N2. And it will map elements in the following way. It will take an ordered pair from G1 cross G2. Let's just call that ordered pair G1 comma G2. And it will map that element to the following. And that is, we'll have G1 times N1 and G2 times N2. It will take it to those cosets defined there. Great. So now we want to consider, is this function a homomorphism? And to do that, let's take two arbitrary elements of our group G1 cross G2. Then we want to apply psi to the product of them and see what we get. So let's go ahead and take those ordered pairs from our group now. We'll call these ordered pairs, let's say G1, G2. And let's say the other one is H1 and H2. Like I said, that will be from our domain G1 cross G2. And we want to consider, like I said, we want to apply psi to the product of them. So we're going to consider psi of our ordered, or the product of our ordered pair, like I said, G1, G2, and H1 and H2. Great. Well, before we actually apply psi, let's actually combine these two ordered pairs using standard multiplication inside of our function symbol there. So that means that's going to be equal to psi of, let's see, we'll have G1 H1 and G2 H2. So now when we apply our function psi to this, we will get the following ordered pair, and that is G1 H1 times N1, and we'll have G2 H2 times N2. And very similarly to how we did in the last problem, we can split that up in the following way. That will be equal to G1 times N1 and H1 times N1. And this will be G2 times N2 and H2 times N2, which we can further split up into the following. The two ordered pairs will have G1 N1, G2 N2, and that will be times H1N1 and H2N2. But we can see that this is exactly equal to phi applied to the ordered pair G1, G2 times phi applied to the ordered pair H1, H2. And that's all we needed to prove that this is in fact a homomorphism. So next, let's go ahead and prove that this function is in fact surjective. But this surjectivity proof is fairly straightforward. So I want to go ahead and note for all arbitrary elements in our codomain, let's just call them G1 and 1, comma, G2 and 2, which is in our codomain, which is G1 mod N1 cross G2 mod N2. We have the following map to the element. So we have that phi of G1 comma G2 is equal to G1 N1 and G2 N2. So like I said, a pretty straightforward map. We took an arbitrary element from our codomain and showed that we could very easily map to it. So because of that, this is surjective, but that means that the image of our function, I wrote phi, but it should be psi, so let me fix that right here. But yeah, that means that the image of our function psi here is equal to exactly what we want, and that is g1 mod n1 cross g2 mod n2. Great, so now all we have to prove is that the kernel is what we need to apply our first isomorphism theorem here, and we will be done. And what we need it to be equal to is in fact n1 cross n2. So let's look at that now. So like I said, we want to look at the kernel of our function here. And so let's consider an arbitrary element of our kernel. And so let's go ahead and consider the ordered pair g1, g2, which is in the kernel of our function, which we've defined to be psi. Great. Well, what does it mean to be in the kernel of psi? Well, that means that if we apply psi to this element here, which is g1, g2, it will be mapped to the identity in our codomain, which in this case is equal to the identity element times n1 and the identity element times n2. Great. But using our definition of psi, this is true if and only if g1 times n1 is equal to the identity times n1, and in parallel, it means that g2 times n2 must be equal to the identity times n2. But this is true if and only if we have that g1 is in n1, and we also have that g2 is in n2. Great, but what does it mean for g1 to be in n1 and g2 to be in n2? Well, that's true if and only if we have that the ordered pair g1, g2 is in the following, and that is n1 cross n2. So here we have the kernel is n1 cross n2, and we have that the image is the entire set. So that means that we can apply the first isomorphism theorem here and prove that these are isomorphic. So just to state what I just said, that means that g1 cross g2 mod out our kernel, which we just found to be n1 cross n2, must be isomorphic to what we calculated for the image here, and that is g1 mod n1 cross g2 mod n2. Great, so that finishes this problem off, so let's go ahead and get into another one. So for this one, we want to make a diagram demonstrating the latticed isomorphism theorem for Q8 mod the set generated by -1. Great, so let me go ahead and remind you what Q8 is, because I think a lot of you are probably not familiar with that group if you're just starting abstract algebra. So the group Q8 contains the following elements: 1, -1, I, j, and k, as well as -I, -j, and -k. Great, but let me go ahead and write that in set builder notation so you understand how this group works. So this group Q8 is generated in the following way. It's generated by the elements, let's just call them the identity E bar, I, j, and k, which have the following relationships such that E bar squared is simply equal to E. And we also have that I squared is equal to j squared, which is equal to k squared, which is equal to I, j, k, which is simply equal to our identity element E bar. Great. So with this in mind, let me go ahead and draw out a diagram demonstrating the lattice isomorphism theorem here. So let me go ahead and start at the top, and that will be the entire group Q8. From here, we will have the following subgroup lattice where we have each of these branches are subgroups generated by the respective elements. The first will have I, then we'll have j here, and then we will have the subgroup generated by k. And all of these are connected to the group generated by -1, like this. Great. And then down here, we will also have the group generated by just the element 1, which is the trivial subgroup. So I want you to note what we're looking for is the diagram demonstrating the lattice isomorphism theorem for Q8 mod the set generated by -1, which means we're only interested in things that are from this -1 and above, and that would be this diagram right here. Great. And so the lattice for Q8 mod -1 will be just the following, and that will be Q8 here, then we'll have the set generated by j, the set generated by k, and the set generated by I here, or the group I should say, and then just the group generated by -1 here, and that is Q8. And we can see that this is isomorphic by the lattice theorem to Z2 cross Z2, which has the following lattice. So the lattice for Z2 cross Z2 is given in the following way, where at the top we have Z2 cross Z2. Then underneath here we have the subgroup generated by 0, 1, Then on the right here, we will have the subgroup generated by 1, 1. And on the left, lastly, we will have the group generated by 1, 0. And then at the bottom here, we will have just the ordered pair 0, 0. Great. So you can see very easily by this diagram, and so you can see very easily from this sketch that we have that these two are isomorphic as their lattices are exactly the same, hence the name, the lattice isomorphism theorem, as we can tell that these two groups are isomorphic just from their lattice. Great. I believe Michael actually did an example of this theorem in the lecture video corresponding to this example video where he talked about how D4 mod out the group generated by R2 is in fact isomorphic to Z2 cross Z2 in exactly the same way. So let me go ahead and get into the next example. And so for this example, we're given a group G, which we're going to define in the following way, and that is denoted by G, comma G in brackets is generated by A inverse B inverse times AB with A and B in G, and this is sometimes called the commutator subgroup. And so what we want to show is that the commutator subgroup for Sn is equal to An. And so because we want to show set equality, we're going to need to show double inclusion here, but we kind of already have the forward direction established for us here, which is given by the following fact. And that fact is that Sn mod out An is commutative. So it immediately follows that the commutator subgroup of Sn is a subset of An from the fact that Sn mod An is commutative. To sketch out a little proof, for n equals 1, this is trivial, but for n greater than or equal to 2, we have that since the order of the quotient group of Sn mod An is equal to 2, and 2 is a prime, we know that Sn mod An is cyclic because it is of prime order, and thus it is abelian, which means, of course, it is commutative. So like I said, it immediately follows from the fact that Sn mod An is commutative that the commutator subgroup of Sn, which we've denoted in Sn brackets here, is a subset of A sub n, which means that what we really want to show is that A sub n is a subgroup of this here, of the commutator subgroup of Sn, comma Sn. Great. So let's go ahead and get into that, I guess, reverse direction here. Great. And so we're going to do this by using the fact that A sub n is generated by 3 cycles, which is a fact I believe we proved in a video we did all on just the alternating group. So you're welcome to check that out if you would like. But like I said, A sub n is generated by 3 cycles. So I'll just abbreviate that, generated by 3 cycles. So if we can represent an arbitrary 3 cycle as a member of this commutator group, we will have done all we need to do to show that A sub n is a subset of the commutator subgroup of Sn. So let's go ahead and look at an arbitrary 3 cycle and see if we can write that. Consider the following 3 cycle. Let's just take an arbitrary 3 cycle 1, 2, 3. But I want you to note that we can express 1, 2, 3 in the following way, and that is that 1, 2, 3 is equal to 1, 2 times 1, 3 times 1, 2 inverse times 1, 3 inverse. Great, and we can see that that is in fact an element of our commutator subgroup as we desire, Sn, comma Sn. And you might say, but in the set builder notation we have the inverses here, but 1, 2 inverse is just 1, 2 inverse inverse, so we are just fine there. Great. So because we've taken an arbitrary element from A sub n, which is a 3 cycle, or rather shown that we can write any arbitrary 3 cycle as a member of the commutator subgroup, we have shown that A sub n is a subset of the commutator subgroup S sub n, comma S sub n. Great. So because we have the forward direction given by the fact that the quotient group of Sn and An is commutative, we have then proven that A sub n is equal to the commutator subgroup of our symmetric group of size n. Great, so let's go ahead and get into our last example. And so for this one, we want to show that GL2R mod out SL2R is isomorphic to the multiplicative group of non-zero real numbers. And so to do this, we are going to need a map which maps matrices into real numbers, and we have a very simple thing that does that, and that will be the determinant. So let's go ahead and define a function so that we can then get working on something that will allow us to apply an isomorphism theorem here. So let's define a function. Let's just call this one phi once again, and phi will go from GL to R to our desired group, which is the multiplicative group of non-zero real numbers, and it will simply map a matrix in GL to R to the determinant of that matrix, which will of course give us a non-zero real number. Great. And so from here, what we want to do is determine if this is a homomorphism. And so let's take two arbitrary elements from our domain. Let's just call them A and B. Like I said, those are going to be from our domain, which is GL to R. And we want to consider the determinant of A times B. So like I said, consider the determinant of A times B. Great. And let's just go ahead and let A be represented in the following way, where A is equal to A1, A2, A3, and A4. And similarly, B is represented by B1, B2, B3, and B4, with our AI and BI being real numbers. So then let's first look at A times B here. So A times B, so we can calculate A times B with simple matrix multiplication, and we'll do that by swiveling in the first row of A to the first column and the second column, etc. I'm sure you know how to do matrix multiplication. So we'll have, for our first input here, we'll have A1 B1 plus A2 times B3. Then swiveling that row into the second column, we will have, for our second input, A1 B2, and that will be plus A2 times B4. And then lastly, we will have our second row into both of the columns there. So that will give us A3 times B1 plus A3 B3. And then for our last input, we will have A3 times B2, and that will be plus A4 times B4. Great. And so then we want to note the determinant of A times B. So the determinant of A times B will be our first input times our fourth input minus our second input times our third input. So let's go ahead and write that out carefully here. So the determinant of AB will equal the following. Well, we will have A1 B1 plus A2 B3 times A3 B2 plus A4 B4. And that will be minus A1 B2 plus A2 B4 times A3 B1 plus A3 B3. Great. And so from here, I want you to note that the product of these things I've outlined in purple will cancel out, as well as the product of the things I will outline in blue, that being this times this and this times this. Great. And so if we look at what we're left with, it should be equal to the determinant of A times the determinant of B, which we can easily calculate here. So let me go ahead and look at that. So what is the determinant of A times the determinant of B? Well, that's very easy to calculate. It'll simply be A1 times A4 minus A2 times A3, and that will be times the determinant of B, which will be of the same form, B1 B4 minus B2 B3. So let's look at what we have left to multiply, and it should be exactly that. You can see that it is in fact what we have left. If we multiply this first term here on the left-hand side into our A4 B4, that'll be what we get when we multiply our A1 A4 into our B1 B4 here. And if we multiply our A2 B3 into our A3 B2 over here, that'll be what we get if we multiply A2 A3 into B2 B3 here, as the negatives will cancel and we'll have a positive result. And the same thing will apply to the right-hand side of our calculation there. So this is good enough to check that this is in fact a homomorphism here. Great. And so now we want to take a look at surjectivity, and surjectivity here is rather easy to prove if we're just a little creative. So for surjectivity, we want to note that for all, let's just call them X, in our X, we have the following map to X, and that is that the determinant of the following matrix, where we have X, 0, 0, 1, is going to be simply equal to x, which is obvious because if you take the determinant of this 2 by 2 matrix, you get x times 1, which is x minus 0 times 0. And so thus we have surjectivity, and that the image of our map, which we have called phi, must be equal to all of our x. Great, so now all we have to do is look at the kernel, but once again, this is pretty straightforward if you know what to look for. So let's look at the kernel. So we want to note that if we take some element which is in the kernel of phi, which we'll just call a matrix A, the kernel of phi, it must satisfy the following conditions, and that is that the determinant of our matrix A must be equal to the identity in Rx, but that is just equal to 1. But if you know your groups well, you'll know that this is simply a definition for SL, in this case 2R, which is exactly what we wanted to prove that the kernel would be, so we can apply our isomorphism theorem here. So let's go ahead and let's go ahead and conclude with our isomorphism theorem here, and that is that GL2R mod out SL2R is isomorphic to our group Rx, which is our multiplicative group of non-zero real numbers. Great, so that finishes this last problem off, and that's a good place to stop.